We've actually done vector components so far. What you just did was vector components. So in bell work, you took that one vector and you broke it up into components, all right? And so as you're going through these vectors, all we're gonna now do is add in more information. The first thing we're gonna talk about is three-dimensional vectors. When you think about three-dimensional vectors, you're just thinking about movement that happens not only east and west, right, on like a plane, but then up as well. Okay, and so we can go east, west, or up for three-dimensional. So it's really the same concept. We are just going to calculate these components individually, all right? So look at the example that they've given us. This says a physics student carries a model rocket from his car 225 meters south and then 275 meters west to the launch site, all right? So south and then west. So if I were to look at this on just a north, south, east, west, first of all, which they gave us a little picture over there to the right. But if I just look here, then I know that he went 225 meters south, right there. And then he went 275 meters west, something like this, okay? So clearly when you have south and west, you have a right triangle. This is easy, all right? Which we could break it down into components if we wanted to. Says this is the launch site. He then launches the rocket to an altitude of 515 meters. If the rocket's displacement vector is d, what is the magnitude of d? And so if you think about this, what we've done here and what they did right here is they created the south 225 and the west 275 right there. So the displacement from where he started at his car all the way to the launch site is going to be the base of our new triangle, the base of our new displacement, right? And so this right here, we need to calculate. We need to calculate that because they've told us how far up it went. They've told us that it went 515 meters in the air. What they're actually asking for is the displacement from his car to where the rocket went, right? So they're asking for this. So we're just going to have to do a twofold calculation. We have to first calculate the ground displacement from the car to the launch site. And then we're going to calculate the vertical displacement, and not meaning vertical on an XY, but now on an XYZ, from the car to the rocket. So it's basically just two triangles is all we're using for this particular one. So how then do I find this guy? Well, that is this right here. What is he of that triangle? What is that? It's the hypotenuse. How do I calculate a hypotenuse if I have the two sides of a triangle? Pythagorean theorem. So I'm going to use the Pythagorean theorem first to calculate this displacement on the ground from his car to the launch site. So what is his displacement there? So if you round to two decimal places, what is the ground displacement from his car to the launch site? Right, you should get 355.32 meters. Does everybody see? And now we have the base and the height of yet another triangle. And so when we're trying to find the overall displacement here from the car, which we're assuming is right here, to how far it went in the air, we're solving for yet another hypotenuse, right? So we're going to take that answer and we're going to square it. We're going to add to it what now? Now we need his vertical movement, which was what? How far up did it go? 515. And then we're going to take the square root of that guy. So overall displacement then is 625.68 meters. Now they did give us, if you look at significant digits, how many significant digits did we use the whole time in addition, subtraction, and multiplication? 3. So if I wanted to put that in 3 significant digits, what would I do? You just round this place right here. That's my third significant digit, 626 meters. So to find this, we're just going to use Pythagorean theorem again with a squared plus b squared equal to that c squared. So we're moving from, believe it or not, that was just one vector kind of that we were solving for, kind of. It's not exactly the same thing that we're going to do. One of those vectors did not actively affect the other vector per se. What we did here is we basically just got overall resultant and then use that resultant to create a new displacement, right? But then there are going to be times when 2 different vectors affect each other. We're going to go first with the example that we used when we were just sketching them with the golfer, but then we're going to do a couple more examples. What happens with your vectors that actually affect each other here is that you have 2 different vectors that are acting independently of each other, but because they are then affecting each other. For example, you have an airplane flying at a specific vector. You have a wind blowing at a specific vector. And so now all of a sudden the airplane is being affected by the wind, right? And so the airplane who had a bearing that they thought they were perfect to get from Charleston to Atlanta per se, if we have a really strong wind that's blowing, they're going to have to adjust what they're doing and their own bearing because that wind is going to affect how that airplane is going. All right, and so those calculations are taking physics into play when they're figuring out how to fly that plane and what bearing they need to use. And so when you start doing this, the first thing you need to do is choose a coordinate system. So we're just going to use our regular coordinate plane, our Cartesian plane. Most of the time when you get these, they're going to be in either map or cardinal. All right, so they're either going to say north of south or they're going to say at a bearing of. Bearing meaning from true north and clockwise, right? Most of the time, these will not be an angular measure other way. For this first part, when we start introducing like force examples, then so sometimes they will say like pulling at a 30-degree angle from the horizontal. From the horizontal means the x-axis when you draw that. And so these are going to typically be directional, either specific directions like cardinal or bearing. Those are the type of examples you're typically going to see for these. Resolve the vector. That just means take those individual vectors that you've been given. Take the airplane's vectors, break him down into his XY movement. Take the wind vectors and break that down into the XY movement, right? So think of this on your quiz like when we sketched them. When you sketched them, you broke it down. You drew one vector, you drew the other vector. And one of the ways I said you could get to that resultant is those individual X's and Y's, right? And so that's what we're going to do with these. We're going to break them down into individual X's and Y's. We're going to add the X's. We're going to add the Y's. That is going to be the movement of my resultant. And from that XY, we can get the resultant's magnitude, and we'll be able to get the resultant's direction as well. You add up all of them, you draw the resultant triangle, you calculate the magnitude and direction. So that's what we're going to do. So the thing that we did at the very beginning when we were talking about sketching them was the golfer. The golfer's first putt rolls 8 meters at 22 degrees north of east. His second shot rolls 2.5 meters at 41 degrees west of north. His final putt rolls due east for 1.1 meters and into the hole. Along which vector should he have putted to make the shot on the first attempt? So when we sketched it, what we ended up with here was 14.1 meters, 3 degrees north of east is how he should have hit that particular ball. And so now what we're going to do, instead of like sketching, and then trying to calculate it, which they will actually tell you to use like a protractor to calculate it. I am not that confident in my drawing skills. Okay, so we're going to do it algebraically, and we're going to break these down algebraically. So what we do is we look at all 3 things that are affecting what's happening to this particular golf ball. The first putt rolls 8 meters at 22 degrees, all right? And they specifically told us north of east, north of east. And so when I look at 22 degrees north of east, it's going to be somewhere right here, all right? Somewhere right there. 22 degrees, this is east, this is north, north of east. 22 degrees is my reference angle, all right? The vector magnitude was how long? How far did that roll is the magnitude. So what is the magnitude for this particular vector? It's just 8 meters. And I'm going to break that vector up into components. So go ahead and break that vector up into your XY components. Your XY components. Meaning, I need to know exactly what, if I were to put a point right here at the end of this, what was my X movement to get there? What was my Y movement to get there? We already know our angular movement. It was 8 meters, 22 degrees north of east, right? I need to know my XY movement there. So you're going to calculate it just like you did in your lab. So I will tell you, when I break these down, I break these into X's and Y's, and I actually write them that way, all right? So what you should have gotten for your X to 3 decimal places was approximately 7.417. Positive. How do I know that's positive? Because I'm using a reference angle. What quadrant am I in? Yeah, my X and Y are positive here. All right. My Y value, rounded to 3 decimal places, should have been 2.997. Which means if I had walked 7.417 meters this way and walked 2.997 meters that way, I would get to that ball. All right? That's what that means. Let's see what else he did. So now he rolls 2.5 meters at 41 degrees, and they said west of north, west of north. So when I do this particular one, I have north, I have west, 41 degrees west of north is right here. What angle am I going to use, though, when I plug this one in? So remember, we are using our reference angle. So we're going to use 49 degrees here. Break that one down into components, X and Y components. A new magnitude of 2.5 meters that you're going to use. So to calculate these, we're just taking the 2.5, which is my magnitude, times the cosine of that 49-degree angle. That's my X value, and my Y value is the same thing, but with sine. So again, why did I put a negative? My calculator did not give me negative 1.640. I am in the second quadrant, so I have to use a negative because that's how the movement of that ball went. All right, let's look at the last one. This final putt rolls due east for 1.1 meters. What's nice about east, west, north, and south is that you actually don't have to use your trig functions at all because the movement is clear. This is not an angular movement. This, well, it is, but it's going to be one of your perfect angles, 0, 90, 180, 270. All right, and so if I'm going due east, here is east right here. Due east is going to be, we'll draw it a little thicker. But due east is going to be right here. And it's 1.1 meters. I know exactly how far I moved in the X direction, and I know exactly how far I moved in the Y direction. In the X direction, due east is exactly what it tells me it is. Right? Positive 1.1. It just told me that. North and south, well, I didn't go north and south because there was no angle given to me. It was a due east, due west, due north, due south movement. And so some of you, when you did your lab, you got like a 90 degree and you were questioning why it was going with one of them as a 0, right? Well, your horizontal movement for a 90 degree angle should have been 0. And the other one was just multiplied by 1 because whatever you went north, That was your vertical movement, right? And so that's what you're going to see when you get directly on that axis. If it had said due west, I would have put negative 1.1 there, right? Due north, then I would have had no horizontal movement and my vertical movement would have been 1.1, right? So you don't even have to use your trig functions when it's on the axis. So then where did the ball end up, right? That's what we need to figure out. We're going to add these up to figure out my resultant. All right, so you're going to add all of your x values, x plus x plus x, including that negative. And then you're going to add all your y values, y, y, and y. What was your x movement? So 6.877. What was your y movement? So 4.884, all right? In this case, whatever the calculator tells you for positive and negative is what you're going to use because you have now combined all the movements. And so you are figuring out where you are on the coordinate plane. What quadrant am I in here on the coordinate plane? If I'm positive, positive. I'm in the first quadrant, right? If I wanted to graph this, let's say I was going 1, 2, 3, 4, 5, 6, 7. My movement over here would be about there. 1, 2, 3, 4, 5. My movement would be about here. So if I were to graph this, it's going to look something like that. Does everybody see that? If I want to know then the direction, so that is my x and y movement. I now need to find how far the ball should go to get there directly and the angular movement of that ball directly. So this tells me my horizontal movement and my vertical movement to get directly from where I putted from to the hole, right? But that's not typically how you putt, right? We don't putt in right angles. Does that make sense? So I need to know the exact length that he should have traveled to get there. I am going to use the Pythagorean theorem to do that. My resultant vector is going to be the square root of my x squared plus my y squared here. That's what it is. This is the movement that I did for x. This is the movement that I did for y, which is a perfect right triangle. So to figure out the direct path length from where he putted to the hole, that is the Pythagorean theorem. So directly was 8.435, and we'll get it down to significant digits. So in the original problem, we had 2 significant digits. So if I bumped this to 2 significant digits, how far is it? 8.4 meters. Now, how then do I find the angle? Well, again, we're going to use something very familiar. We're going to use trig. I'm trying to find this angle. Remember, the reference angle is what I'm finding. How I give it to you is going to be how they gave me direction to begin with. But we're going to find the reference angle at first, right? Well, if that's my angle, then my y value is my opposite. My x value is my adjacent, which is, by the way, how it will always be for reference angles. What trig function deals with opposite and adjacent, or y and x movement? Tangent. I am solving for the angular movement. When you are solving for the angular movement or the angle on your calculator, which button do you use? Your inverse button. So in the calculator, to figure out the angle measure that this ball should have gone, we're going to use the inverse tangent of that y over the x. Always the y over the x, and it will give you the reference angle. So make sure you do inverse tangent. It will open parentheses. Keep those parentheses open for that division. Your y is 4.884. Your x is the 6.877. Then you can close parentheses and get that angle. So if you use it in significant digits, we just have 35 degrees. Now here's the thing. 35 degrees tells me in standard position, meaning coordinate plane, Cartesian plane, counterclockwise, right? That's what it's telling me. However, that's not how they gave me my directions. So I'm going to go back to how the word problem was written. So if I said 35 degrees here, I would say north of east. Does everybody see why I would say north of east? That is how you tell me where that actually is. Because 35 degrees, you could get 4 different places on this coordinate plane. You could get it in the first quadrant, second, third, or fourth, because I am finding reference angle. And so you need to be more specific. So you want to say north of east. If they had given it to me in bearing form, from north clockwise, you want to go back and give me the bearing after you find that reference angle. So that's why sketching it helps you. That's why knowing what quadrant you're in helps you. An airplane is traveling at a fixed altitude with a negligible wind factor, heading 30 degrees north of west at a speed of 500 miles per hour. The airplane encounters a wind with a velocity of 70 miles per hour in the direction of 45 degrees north of east. What are the resultant speed and direction of the airplane? So when you have something like this, clearly your direction is given to you in degrees by some method. In this case, the heading is a bearing, and then the other one is given to you in a cardinal way, right? North of east. The miles per hour is your magnitude. Your miles per hour here is your magnitude. All right? So we're going to sketch the airplane. We're going to sketch the wind, and then we're going to find that resultant. All right? So sketching the airplane then, they have told me it is a heading of 30 degrees. That is a bearing that they have given me. A heading is a bearing. So we're going to start at true north. We'll say north of west. That's going to be much better if we actually do the right bearing. So we're going to say north of west. That puts us there. And now we get to use the 30 degrees that they gave us and 500 miles per hour. Which makes sense. My wind, 70 miles per hour north of east. So it is 45 degrees north of east. North of east is right here. What's nice about 45 is wherever they give it to me in that quadrant, it's also going to be my reference angle. In this case, it's what they gave me, 45 degrees. So break those two down into components. Give me the components of the airplane. Give me the components of the wind. So for the first one, I use negative, positive. For the second one, positive, positive, because of what quadrant I was in, right? And now you want to find your resultant xy. So add your x's, add your y's. So you should have gotten negative 383 approximately and 299, positive 299 with some decimals in there. So what quadrant is this plane going to be in? The second quadrant, which makes sense. He was going a lot faster than that wind was blowing, right? So even though the wind was kind of blowing directly against it, it makes sense that if he was traveling this direction and he had a wind blowing against him, like if you were to grab this and slide it, it's pushing it that way. So it makes sense that he wouldn't go as far west and he would go farther north. Like it makes sense. Think about if it were pushing on it from that direction. It would push it up, which would pick this vector up higher closer to the X on the X-axis horizontally, farther away vertically, which is what we ended up with. Closer to the origin, farther away, right? So we're going to find out how far it actually traveled and the angle that it traveled, the direction that it traveled. So how far is going to be the magnitude? We're going to go back to Pythagorean theorem, x squared plus y squared square root. He was going with the wind blowing against him. It slowed him down, right? He originally was set at 500 miles an hour, but the wind is slowing him down. He's going 487 miles per hour. Now, the wind has also affected his direction, right? He was going 30 degrees north of west. Now we're going to calculate his actual direction that happened with a tangent, all right? So we're going to say the inverse tangent, because once again, we are solving for angle. Inverse tangent of my y divided by my x. You can also ignore the positives and negatives. Ignore the positives and negatives because we're just talking reference angle here. We're just talking reference angle. So we're going to sketch the reference angle on these. So do inverse tangent, ignore your positives and negatives, 299.497 divided by the x value, 383.516. And it is going to give us the reference angle. What reference angle do you get here? All right, so you should have gotten about 38 degrees, all right? But we need to figure out where we're going to graph this. This has given us 38 degrees to the closest x-axis. In which quadrant? Go back here. What quadrant did we say we were in? The second. So it has given us this angle measure 38 degrees away from my x-axis in the second quadrant. That's what that calculator has given me. Here's why this is important. Now, when I'm talking map direction, cardinal direction, that's very simple. I'm going to write he was going 487 miles per hour, 38 degrees. How am I going to describe that cardinal? How am I going to describe that? North of west, right? North of west. This is west, this is north. I am traveling 38 degrees north of west. Had they given me a bearing, at the beginning, then I would need to go back and say, oh, it's going to be 90, 180, 270 plus 38 if they had given it to me as a bearing. Does that make sense? So go back and give it the answer the way they gave it to you to begin with. They gave us cardinal, we're going to give them cardinal. Had they given us map or a bearing, we would give them the bearing.